Okay, in this video, this is going to be the second video for section 6.3 on Taylor and Maclaurin series and polynomials. We're going to be looking at Taylor's theorem with the remainder, and this is going to allow us to figure out how good of an approximation our Taylor polynomial is going to be at a certain point. And then we can also use it for proving that power series converge to certain functions, and specifically where does the Taylor series converge to its function. So Taylor's theorem with the remainder says that let f be a function that can be differentiated n plus 1 times on an interval I, containing the real number a. Let p sub n be the nth Taylor polynomial of f at a, and let r sub n of x equal f of x minus p sub n of x. And so that's going to be the remainder, the part that where the Taylor polynomial and the function are not in agreement. The remainder will be the part that makes sure that they are equal. Be the nth remainder. Then for each x in the interval I, there exists a real number c between a and x, such that the remainder, the nth remainder, is going to be equal to the nth plus 1 derivative evaluated at c over n plus 1 factorial x minus a to the n plus 1. If there exists a real number m such that the nth derivative evaluated at x, so let's go ahead and put that in there, evaluated at x is less than or equal to m for all x in the interval I, then the remainder in absolute value is going to be less than or equal to m over n plus 1 factorial x minus a to the n plus 1 for all x in I. And this is going to give us a bound on the remainder, or our error here. And then if that error goes to 0, then we can do things like prove power series, specifically Taylor series, converge to functions. Okay, so let's go through the Taylor's theorem. Okay. So it says, for the proof, fix a point x in the interval I, and let g be a function such that g of t is equal to f of x minus f of t minus f prime of t x minus t minus f double prime of t over 2 factorial x minus t squared minus dot 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 minus the nth derivative evaluated at t over n minus 1 factorial x minus t to the n minus 1 minus the nth derivative evaluated at t over n factorial x minus t to the n minus the nth remainder times x minus t to the n plus 1 over x minus a to the n plus 1. And so this is a construction here, and we're going to use this g function, and we want to show that g satisfies the Rolle's theorem. Rolle's theorem stated that if the endpoints were equal to 0, so g of x and g of a, if those were both equal to 0, we have a continuous function on the closed interval, differentiable on the open interval, then we would know that we have a horizontal tangent. So we want to show that g satisfies Rolle's theorem. That is to show that g of x is equal to 0 and g of a is equal to 0. And we know that g is a polynomial function of t, so it is continuous and differentiable. The conclusion is a c between, there exists a c between x and a such that g prime of c is equal to 0, and that's your horizontal tangent. So if we evaluate the function at g of a, well, you're going to have f of x minus f of a minus f prime of a x minus a minus f double prime of a over 2 factorial. Oops, and this should say x minus a, not a minus x. Okay, all the way out to f of n evaluated at a, the f derivative of f evaluated a over n factorial x minus a minus the nth derivative, not the nth derivative, the nth remainder. And so what we got going on here is this is the nth degree Taylor polynomial, and this is the remainder for it. So the remainder plus the nth degree Taylor polynomial is going to be equal to the function. So you have the function minus itself,
and so that's 0. If we plug in x into the function, then it's going to be f of x minus f of x minus f prime of x times x minus x. And so all of those remaining terms are going to cancel out. And so we have g of x is also equal to 0. Thus, Rolle's theorem is satisfied. Not satisfies. So there exists a c between a and x such that g prime of c is equal to 0. So we're going to take the derivative with respect to x. So the derivative of f of x would be 0. Derivative of f of t would be f prime of t. Derivative of f prime of t x minus t, so that's a product. So take the derivative of f prime of t, that'll be f double prime of t times x minus t. And then f prime of t, and then we need to take the derivative of x minus t. That's your product rule. So f prime of t is there. Derivative of x minus t with respect to t will be 0 minus 1. Okay, then take the derivative of the next one. So we have another product. So derivative of f double prime of t would be f triple prime of t over 2 factorial x minus t squared. Then take the derivative of the second function would be the x minus t squared. So the first function, the same, is the f double prime. So here's the one we just talked about. So we got f double prime of t over 2 factorial. The 2 comes down, x minus t to the first power times negative 1. Now if we go all the way out to the n minus 1 term right here, if we take the derivative of that, so take the derivative of the n minus 1 derivative at t, that'll become the nth derivative at t, times x minus t to the n minus 1, and then we'll leave this alone, and then times the derivative of x minus t to the n minus 1. So the n minus 1 comes down, x minus t to the n minus 2, and then times negative 1 by the chain rule. Now let's take the derivative of the nth portion here. So the derivative of f of n of t would be the n plus 1 derivative over n factorial x minus t to the n. And then it is a product rule, so then we're going to leave the nth derivative of t evaluated n alone, and then take the derivative of the x minus t to the n, so that n would come down, and we'd have x minus t to the n minus 1 times negative 1 by the chain rule. Okay, and then we'll take the derivative of the remainder portion, so it's with respect to x, so r sub n of x is going to be a constant, the x minus a to the n plus 1 in the denominator is a constant. So we take the derivative here, the n plus 1 will come down, x minus t to the n times negative 1. We do have some double negative action going on, so that part is going to be positive. And then we'll notice some canceling going on. So the f prime of t, negative f prime of t, and positive f prime of t will absorb. Okay, the f double prime of t times x minus t will absorb. The nth derivative evaluated at t over n minus 1 factorial x minus t to the n minus 1 will absorb. Okay, and then certainly the other two terms are going to absorb that we don't really want here. This term here will absorb with another term further along. This one will absorb with a previous term. And so what we have left is the n plus 1 derivative evaluated at t over n factorial x minus t to the n, and we have positive the nth remainder times n plus 1 x minus t to the n all over x minus a n plus 1. So that's our telescoping effect. Okay. All right. So now most of the terms will cancel out because of the telescoping effect. So g prime of t is equal to negative n plus 1 derivative of t over n factorial x minus t to the n plus n plus 1 times the remainder, nth remainder, times x minus t to the n over x minus a to the n plus 1. By the Rolle's theorem, there exists a c between a and x such that g prime of c is equal to 0. So g prime of c is equal to negative n plus 1 derivative evaluated at c over n factorial, so that'd be negative of that, x minus c to the n plus n plus 1 nth remainder
times x minus c to the n over x minus a to the n plus 1 is equal to 0. And if we solve that for the remainder, that is going to give us the nth plus 1 derivative evaluated at c over n plus 1 factorial times x minus a to the n plus 1. So if there exists a real number m such that the nth derivative evaluated at x is less than or equal to m for all x in the interval I, then we can have a bound on our remainder. So our remainder in absolute value is less than or equal to m over n plus 1 factorial x minus a to the n plus 1. That'll tell us how good of an estimate we have going on, and we'll do an example of that. And we can also use this result to prove that a Taylor series converges to a particular function. So let's try that out in a couple examples here. So we'll look at example number 4. And we're going to find a 6th-degree Taylor polynomial centered at x equals 0 for f of x is equal to the cosine of x. So this will be a Maclaurin polynomial. And we're going to use it to find an approximation for the cosine of 0.1. And then we want to use the Taylor's remainder theorem, the remainder portion, to see how good of an estimate it is. So we're going to find an upper bound for the error. Okay. Alright, so we're going to start off with f of x is equal to cosine. And we'll take the first derivative, which is minus sine, and the second derivative, which is minus cosine, and the third derivative, which is sine. Fourth derivative, we're back to cosine. Fifth derivative is back to minus sine. And the sixth derivative is back to minus cosine. And so now we're going to evaluate each one of these at 0. So the original function at 0 is 1. First derivative at 0 is 0. Second derivative at 0 is minus 1. Third derivative at 0 is 0. Fourth derivative at 0 is 1. Fifth derivative at 0 is 0. And the sixth derivative at 0 is going to be minus 1. So our 6th-degree Taylor polynomial is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And so we're going to use this polynomial here to make an approximation for the cosine of 0.1. So the 6th Taylor polynomial evaluated at 0.1 is going to be 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus 0.1 to the 6th over 6 factorial, which is going to be approximately 0.99500416527, etc. Okay. Now the n plus 1 derivative is going to be a sine or cosine in an absolute value, and sine or cosine is going to be bounded by 1. So we can have a bound for the n plus 1 derivative at x that's going to be 1. So the 6th remainder in absolute value is going to be less than or equal to your bound, which is the m, over, sorry, that should be a plus 1, over 6 plus 1 factorial, and then 0.1 minus 0, so that's your x, which is 0.1, centered at a, which is 0, so that's where the 0.1 minus 0 comes from, raised to 6.1. So the upper bound of your error is going to be, after we calculate that, 0.000, so we got a whole bunch of zeros. So that's our upper bound for our error. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the approximation should be good up to at least 10 decimal places. That's how good this approximation is. At least 10 decimal places. So this is an upper bound of our error, so it needs to be as good as 10 decimal places. Okay. So accurate to 10 decimal places at least. So the cosine of 0.1, if I use my calculator, I got to make sure I'm in radians, is approximately 0.995004165278025. And if we count that up, let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think the next one in this decimal expansion is a 7. I think it's 7 repeating. So we're accurate up to 11 decimal places. So the Taylor's remainder portion said we'd be accurate at least to 10 decimals, and that was an upper bound for the estimate of the error. So we're okay. So we're accurate up to 11 decimal places. And if you want a more accurate result, go ahead and use a higher ordered Taylor polynomial. Okay. All right. So that's one application of the Taylor's remainder theorem. So the next thing we're going to look at is looking at a series and maybe figuring out what the Taylor series for cosine is. So let's go ahead and show for a fixed x that the sum n equals 1 to infinity of x to the n plus 1 over n plus 1 factorial converges. So we're going to use the ratio test. So the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute value. So the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial divided by x to the n plus 1 over n plus 1 factorial. So it's going to be the limit as n goes to infinity of x to the n plus 1 times x over n plus 2 times n plus 1 factorial times n plus 1 factorial over x to the n plus 1. So that's going to be equal to the limit as n goes to infinity of the absolute value of x over n plus 2, and that's going to be equal to 0, which is less than 1. And this shows that this converges for this particular value of x. And so we have converges absolutely. And then we would call this pointwise convergence here. Okay, so converges absolutely by the ratio test. Now, if we know that the sum n equals 1 to infinity of x to the n plus 1 over n plus 1 converges, then what that tells us is the sum, and that tells us that the limit n goes to infinity of x to the n plus 1 over n plus 1 factorial is equal to 0. And that's the contrapositive of the nth term test. The nth term test says that if this is not 0, then this would diverge. So the contrapositive would be if the series converges, then the limit of the seed sequence goes to 0. Okay, and so we're going to use this result for proving something about the cosine. Okay, so for a fixed x, the nth remainder of x is equal to the cosine x minus the nth Taylor polynomial. And what we want to do is we want to show that the limit as n goes to infinity of the nth remainder of x is equal to 0. So we know that 0 is less than or equal to the absolute value of the remainder, which is going to be less than or equal to m. So m over n plus 1 factorial x minus a to the n plus 1, and that's where m is going to be the bound on the nth derivative of f of x. Okay, so for our specific example, the nth remainder is going to be bounded between 0 and Well, m for the cosine, the nth derivative of cosine is going to be either plus or minus sine or cosine. Those are all bounded by 1. So the m would be 1. And then we're going to center this at 0. So the x minus a would be x minus 0. So that gives us the n plus 1 over n plus 1 factorial. We do need to put the absolute value bars on x. Okay. Now, we know that the limit as n goes to infinity of 0 is 0, and the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial, that's going to be equal to 0. Okay, so by the squeeze theorem, the limit as n goes to infinity of the nth remainder is going to be equal to 0. And so that's what we want. And so the nth, and so that means the cosine is going to converge to its Taylor series, if I can say series. Say series 3 times fast. Series. All right, so let's go ahead and just for our reference put up the 6 degree Taylor polynomial again. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we can write this as the sum n equals 0 to 3 of negative 1 to the n, x to the 2n over 2n factorial. And that is the 6th degree Taylor polynomial. It's actually a Maclaurin polynomial because we're centering it at 0. And then specifically for the cosine. Okay. So we can also write it like this: sum n equals 0 to 6 of the nth derivative evaluated at 0, x to the n over n factorial. Okay, so cosine of x is equal to the nth degree Taylor polynomial plus the remainder portion, and that's going to go to the sum n equals 0 to infinity of the nth derivative evaluated at 0, x to the n over n factorial. And we showed previously that remainder is going to go to 0. Okay? And plus 0 as n goes to infinity. So here's your Taylor series, and here's your remainder going to 0 as n goes to infinity. So the cosine of x is equal to the sum n equals 0 to infinity of the nth derivative evaluated at 0, x to the n, all over n factorial. Okay, and so let's write out some terms. So that's going to be 1 plus 0x minus x squared over 2 factorial. And if you remember, we started with cosine. Derivative of cosine is minus sine, and derivative of minus sine is minus cosine, and derivative of minus cosine should be positive sine. Okay, and so we're evaluating it at 0, so the cosine of 0 is 0. Cosine of minus, the negative sine of 0 is 0, so that's where we get oops, wrong one. That's where we get the 0 here. Okay, and then the negative cosine of 0 is negative 1, so that's where that minus 1 is coming from. And then the sine of 0 would be 0, so our next term would be 0x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... We'll put the x to the 5th in there, and the x to the 6th, etc. So we can write the cosine of x is equal to the sum n equals 0 to infinity of negative 1 to the n, and all our powers of x are to the 2n power, and same with our factorials. They're going to be 2n factorials. And so here's our Maclaurin series of the cosine, which is equal to the sum n equals 0 to infinity of negative 1 to the n, x to the 2n times 2n factorial. Now we know this, so we can do cool things like we could take the derivative of this, and we could get negative sine, and we could get the power series for minus sine. We could integrate this thing, and we could get the power series for the sine, because the antiderivative of cosine is sine. So anyways, Stay tuned for the last video on this section 6.3. We'll see you next time.